Good afternoon, everyone. It is my great pleasure to introduce our resource person, Dr. C. Balamurugan. He is an associate professor in the Department of Electronics and Communication Engineering at National Engineering College, Kovilpatti. With more than 17 years of teaching and research experience, he obtained his BE, ME, and PhD degrees from Anna University, Chennai. His area of research interest include microstrip and wearable antennas, RF and microwave engineering, nanomaterial-based antenna substrates, frequency selective surface, and wireless communication system. He has published 15 plus research articles in reputed SCA and Scopus Index journals, including International Journal of RF and Microwave Computer Aided Engineering, Wireless Personal Communication, International Journal of Communication System, and scientific reports along with several papers in leading international conference. He holds 2 Indian patents in the area of IoT-based system and agricultural instrumentation. He is actively guiding 5 PhD research scholars under Anna University and has organized IEEE sponsored workshop and seminars. He has also delivered expert lectures and hands-on training programs and antenna design, simulation, and fabrication using electromagnetic simulation.
Very good afternoon to one and all. I hope my screen is visible.
That is visible, sir. So, do you hear me?
So thank you very much for showing interest and learning antenna design using nanomaterials. Today I'm going to present about that is using nanomaterial, that is using antenna design using nanomaterials. Actually, nowadays antenna, that is as a researcher, what we are doing, what people are doing is that's by suitably designing the geometry or changing the geometry of the patch. Generally, I'm speaking about planar antenna. By changing the geometry of the patch, one can modify that one can achieve the required specifications. Required specification in the sense that is mostly we focus on, that is achieving reasonable gain, achieving the suitable polarization, okay, achieving the dual polarization agility. Like that only we focusing most of the applications. In case if you go for the antenna design for aircraft and spacecraft applications, we will focusing in that aspect only. But antenna, by changing the geometry of the antenna, one can achieve the desired specification. There's nothing there is no alternate in this. But from my point of view, by suitably designing antenna, by designing antenna using suitable nano material, one can achieve the better performance. Okay, that is my point of view for the today presentation. That is the presentation outline. Let me proceed from the beginning of it. Actually, it is very convenient to start from the historical background of the antenna. That is, era of electromagnetism was started in the year of 1785 by Coulombs. Okay, he invented a force between the two electrically charged particles. Okay, the force may be positive, that is repulsive force or attractive force, that is depends upon the polarity of the charges. So he invented that force is inversely proportional to the square of the distance between the two particles. That is the very first invention in this era of that is history back external work of the antenna. And then Ampere he discovered the relationship between the electricity and magneticity in the year of 1820. Just Maxwell, actually, he is the father of the electromagnetic wave from my point of view. Actually, what he did is he relates the Coulomb's finding and Ampere's finding, and he relates this Coulomb's finding, Ampere's finding with the Stokes theorem, and he invented that is electrical and magnetic fields are perpendicular to each other. So before the invention of Maxwell, Coulomb's did research work on electric field, Ampere's did research work on magnetic field. Maxwell is the first person, he relates the Coulomb's law and Ampere's law by using the Stokes theorem. That is the finding here. The electric and magnetic fields are perpendicular to each other and can travel through the free space at the speed of light. This is the very first invention. After this Maxwell findings only, there are so many inventions that is happens in the antenna domain. Further, Maxwell showed the relationship between electric and magnetic through 4 different equations. That is a del dot D, del cross E, and he related that is a that the time varying magnetic field produces the electric field, vice versa. Actually, he related electric field and the magnetic field. That is a finding of Maxwell. After the Maxwell finding, that is Heinrich Hertz demonstrated this Maxwell equation so by inventing an antenna in 1888. After that, in 1980s, that is antennas are emerged for various wireless applications. Nowadays, the planar antennas are more familiar for researchers because it occupies very less space and low profile antenna, low cost and easy to mount. These are some of the advantages of microstrip patch antenna. In our case, that is we focus on wearable, the IoT and 6G applications. In IoT 6G application, antenna should occupy very less space, right? From the user point of view, that is from the user terminal point of view, antenna should occupy very less space. So patch antenna, planar antenna is a very suitable one for this applications, 6G and IoT applications. This is the evolution history of antenna. That is, wire antenna is invented by Heinrich Hertz. In the name of Hertz, actually, there is a frequency, the unit of the frequency is Hertz because of his invention. Actually, he's the first person he verified the Maxwell's theory by using dipole antenna. He also invented parabolic reflector antenna in 1888. And the phased array antennas principles originally invented by Sidney Brown in the year of 1889. Nowadays, phased array antennas are more familiar in most of the applications. And Hahn antenna, that is proposed by our Indian scientist, Sir Chandra Bose. Actually, he is from IIT Kharagpur. He invented Hahn antenna, that is open-ended waveguide. This Hahn antenna finds more application in aperture antenna-based application in the year of 1895. In 1897, that is the biconical antenna, dipole antenna is invented. And the Yagiuda antenna invented by Yagiuda. The Margoli is the father of wireless communication. He invented monopole antenna. Monopole antenna, that is a case. He verified the monopole antenna. And the microstrip patch antenna is invented in 1953. After that, so many inventions in the patch antenna and the different varieties of patch antennas also there. Actually, our focus is that is application of nanomaterial for the antenna design for that is high frequency applications. And actually ceramic materials, actually there are nano materials mostly from ceramic family that is finds more applications in antenna design. There is non-ceramic materials, it's micron sized alumina, aluminum nitride, there is silicon nitride. Those materials are utilized, that is in literature. These materials are preferred by the many researchers for antenna design. They're successful materials. But ceramic materials such as aluminum ceramic, aluminum nitride ceramic, boron nitride, that also be very that is a very useful substrate material for antenna design. Why ceramic material is being preferred over other materials? Ceramic material has that is a high dielectric constant. It has a very low loss. That's why most of the in recent years, there is a materials being preferred from the ceramic family only because of these advantages. In addition to that, nano and compound materials also played a major role in patch antenna design. That also being used by the that can be used for antenna design by the literature, from the literature. So regarding wearable antenna actually essential for most of the that is body wearing applications. That is W-band healthcare monitoring and smart tech. So these antennas are being preferred. And actually, unlike the conventional antennas, that is a rigid antenna. Okay, these antennas are not under bending, right? Even bending, we can use this antenna. And movement and the temperature variation, different temperature variation to antenna, this antenna will be can be operated. Antenna performance is highly influenced by the type of substrate material being preferred. So conventional rigid substrates are unsuitable for wearable environment, right? So if a wearable application, antenna should bend. Okay, if the antenna can be mounted, that is any part of the body. Even a helmet mounted antenna there, textile antenna there, okay, wristwatch antenna there, built. So many antennas are invented for body wearable applications. In most of the cases, antennas should operate while bending, right? While bending. So this flexibility is not available with conventional rigid substrates such as FR4 substrate or Rogers substrate. The substrates cannot bend. Those substrates are rigid substrate. So those substrates cannot be preferred for the wearable antenna design. And why substrates is matter in wearable antenna? Substrate actually forms the electromagnetism generated between the patch and ground. Substrate dielectric constant, that is directly influences the antenna size and frequency. That is, antenna size is directly proportional to the dielectric constant. So we know that that is a model of the antenna, transmission line model of the microstrip patch antenna. Okay, size of the antenna, that is mostly depends upon dielectric constant of the substrate. Frequency of the antenna, that is also influenced by the dielectric constant. That is also done by actually this is the frequency tuning can be possible by changing the dielectric constant of the substrate. By using this this principle only, antenna, that is by changing the, that is temporary, that is by changing the dielectric constant, frequency will happen. So using this principle, the microstrip patch antenna can also be used as a sensor. In recent year, you can see so many applications, so many papers in the domain of patch antenna using temperature sensor, some other sensor. That is also possible using the, and using this property. And the substrate thickness affects the bandwidth and radiation efficiency. The height of the substrate plays a major role. By slightly modifying the height, by slightly adjusting the height, one can alter the bandwidth of the patch antenna also. Not much of 0.1% or 0.2% of the height is increased. By increasing that is height by 0.1, 0.2%, one can modify the bandwidth of the antenna also. That is also possible. And the wearable antenna actually demands maintain stable electric field during bending. That is required. That is a temperature dependent substrate behavior can resonate shifts that can be done by using this temperature dependent principle. So so in this way, in this substrate plays a major role. Okay, substrate actually affect the most of the important parameters of the antenna. It affect the bandwidth, it affect the radiation efficiency. Okay, it also it also affect the antenna size. So these are the critical parameters for wearable antenna. Antenna is the most important parameter. Antenna bandwidth, that is also another. These the parameters can be controlled by using the suitable substrate. So these are the substrate material being preferred in wearable antenna design. Actually, commercial, that is, these are the substrate material that are available in literature. That is flexible PCB that is available. Textile materials are available substrate for the patch antenna design, and polymer substrate. These substrates are available. Textile, there are so many varieties. Polymer also there are so many. But out of all these polymer, PDMS polymer is most familiar. In most of the cases, PDMS polymers finds this it has a very low loss, and you can use this PDMS polymer by using this material, by adding another nanomaterial, another material with PDMS substrate polymer material. One can invent new substrate. That is also possible. That is the focus of our day presentation. So, okay, before to start thinking about the antenna design for 6G application, key requirement, see 6G characteristics impacting IoTs. It requires that is data rate to be supported in terms of terabits per second. These are the common thing already we know, right? Ultra low latency, that is also main requirement, and extremely device sensitivity, AI native network, integrated sensing and communication, and energy aware batteryless. These are the key 6G characteristics which impact the IoT. Okay, wearable antenna from the antenna point of view, the wearable must be for this application should be lightweight, and it should be flexible and stretchable. For wearable, it should be flexible and stretchable, and it conformal to the human body. Antenna must merge with the cloth, skin, and accessories. And also, antenna that is designed for 6G applications should be multi-band and ultra wideband operations. So actually, since 6G applications are available, it occupies from sub 6 gigahertz and millimeter wave frequency band, sub terahertz applications. Antennas should operate at different frequency bands. Same antenna. It is more that is another useful thing is the antenna that is not only used for single frequency. Antenna can operate in multiple frequencies. That is also required one for this application also. Antenna should be reconfigurable. That is another thing. It should be reconfigurable. And the multi-band antennas are mandatory for these applications. So antenna must ensure the stable impedance tissue and the low SAR and pattern robustness. These are the antenna should have this property. Wearable will not only transmit data, but also it can be used as a sense motion, monitor vitals, enable local. These are some things about the wearable antennas and things. So these are the evolution of wearable antennas. The first generation, it used this based on the rigid wearable antennas, such a microstrip patch, monopole. These are the actually by designing patch antenna, by using a compact patch antenna, they used this antenna for wearable application by using very short, very compact antenna. The second generation antenna for wearable application, okay, the antenna should be bent, right? For that, they use the textile antenna. Textile material is used as a antenna substrate. And also it is very comfortable than the first generation antenna, and it is sensitive, but the problem is it's sensitive to moisture, washing, and bending. And the third generation uses the polymer material as a substrate for the wearable antenna design. And 4G, 5G, 6G application, also advanced antennas. Actually, these are nowadays antennas should be reconfigurable in frequency, pattern, and polarization. Reconfiguration can be possible by using pin diodes in the design. Pin diodes, varactors, and MEMS devices, metamaterials. These are these things. It comes into picture for 6G applications. To adapt to body and environment, multi-band support. These are the evolution of wearable antenna from generation wise. So 6G oriented intelligent wearable antennas it has to have some of the key features. It should be AI assisted adaptive antennas, terahertz compatible materials, and integrated sensing and communication, self-healing and stretchable structure, low SAR metasurface background design. So for this, what about we wish to prefer the nanomaterial for the 6G application? That is the content of your presentation. Why nanomaterial substrate for 6G wearable? That is we have to answer. What are the nanomaterial substrate? Why is substrate matters for more high figure? These are the question we need to answer before to start with the antenna design using these materials. Before to discuss with the that is a wearable antenna that is using nanomaterial for the wearable antenna, let me discuss about the patch antenna design using nanomaterial. This antenna is for rigid antenna is a rigid uses rigid substrate only. Then let us focus on how to convert this rigid into flexible for IoT and 6G applications. First of all, actually, in this presentation, I'm mentioning it's a hexagonal boron nitride substrate. The HBN ceramic substrate is a used substrate for this case study. This substrate material is imported from Canada. The average article size of the HBN nanoparticle is 17 nanometer, and also in this work, this powder metrology technique is preferred for preparing the substrate. So powder metrology technique is nothing but that is a HBN material powder is compressed using compression testing machine. Okay, by using specially designed tie setup. Then substrate is annealed. That is a compressed substrate is a green substrate. And it should be annealed at the temperature of 80 degree to convert into rigid. After this annealing process, sintering process is done at a high temperature to strengthen the substrate. Finally, it's cooled down under nitrogen gas. So these are the process involved in the powder metrology technique. So raw powder imported from this company is used. The powder metrology technique is used to convert this powder material into substrate. So in this way, I'm doing this by using compression testing machine, sintering process. We can convert, we can prepare a substrate for the required specifications. This is the sample copy of compressor testing machine. Okay, here powder material is compacted by placing it in the specially designed tie setup. Okay, with the pressure of 200 megapixels applied to the powder, and then after that annealing is done using the high temperature furnace to remove the internal pores present due to the unavoidable defect during compactness. There is a setup process of sintering process, and here there is a prepared substrate. Prepared green substrate is sintered at high temperature using tubular furnace for 2 hours with the nitrogen atmosphere. Sintering process is required to strengthen the prepared substrate and increase the structural integrity of the HB nano ceramic substrate. After the sintering process, this is the prepared substrate. The prepared substrate has a 15 millimeter diameter, 50 millimeter. So from this prepared substrate, beside rectangular patch with the dimension of required dimension is cut from the above prepared substrate, which is being used as a substrate for the patch antenna design. And the thing here is sintering temperature plays a major role of the antenna design. Actually, by varying the temperature of the sintering process, one can vary the dielectric constant. This I have experienced from my research work. So actually, by performing sintering at 1600 degree, dielectric constant is 5.1. By decreasing the sintering process, one can alter by varying the sintering process from 800 to 1600, one can achieve the desired dielectric constant for the required specifications. The thing is, the dielectric constant decreases with increasing the sintering temperature. So prepared substrate is to be characterized using these techniques, that is scanning electron microscopy and X-ray diffraction, Fourier transform infrared spectrography, and some with EDAX, and finally capacitance of the material also will be determined using the LCR meter. This is the XRD pattern for the diffused raw powder material and the prepared substrate. Actually, it seems that from figure A and B, it seems that the same pattern is observed for both the prepared substrate and received hexagon boron nitride powder. This FTIR image of the prepared substrate and nanoparticles, and figure shows that it confirms that there is a presence of HBN substrate. That is what I'm saying is after this by sintering process, there is a HBN boron nitride that is properties retained even after the sintering process. So we can confirm the statement from this figure. This is some with EDAX image of the prepared substrate and materials. So this figure, we can infer that that's maximum peak intensity of the nitrogen boron elements. We can confirm that tested ceramic powder has hexagonal boron nitride as ceramic substance, and highest and it observed the hexagon based ceramic substrate has not been subjected to any chemical changes while preparing the antenna substrate. This study is required if we prefer the new substrate. If we do the if we propose new substrate for the antenna design, so we need to study the prepared substrate using this characterization technique. Then antenna, there is the analysis of antenna using prepared hexagonal ceramic substrate material. I'm answering these 5 antenna parameters, conventional antenna parameter, which defines the performance of the antenna. This is there is a designed substrate using the HFSS model. This is the reflection coefficient parameter of the that is designed antenna. This antenna achieves resonance at 2 different frequencies at 2.2 GHz and 2.6 GHz. Antenna achieves wide bandwidth for the given specifications. And SF, the voltage rating ratio is another important parameter. That is ideally, and VSWR values be closer to 1. There is antenna designed using the hexagonal boron nitride achieves the patch antenna VSWR, the patch antenna, which is very closer to the ideal value. The ideal value is 1. That is by using this SVN ceramic substrate. That is VSWR actually is very closer to ideal value. That is 1.02. This is a gain plot of the proposed antenna. Antenna achieves a higher gain, that is 8 dB at a frequency of 2.6 GHz. So from the graph, you can infer that there is prepared substrate not performing well at the low frequency. The low frequency of the radio spectrum, that is from 1 to 2 GHz, antenna achieves a very low gain. Whereas for higher band of the simulated antenna, that is from 2 to above 2 to 3 GHz, antenna has a significant gain. So from this, because of this antenna has some more losses at low frequency. This prepared substrate performs well at the high frequency band of the S band. So radiation efficiency confirms this low gain at the low frequency range. Antenna achieves maximum radiation efficiency of 78% at the resonant frequency. This is a reflection coefficient, that is comparison of that is a simulated result with the measured result. Measured result shows that antenna achieves good impedance match. Okay, there is a good degree of matching between the simulated and measured results. At that low frequency, this figure indicates that low frequency measured result shows that one more resonance at the frequency about 1.75 GHz. These are due to losses. Actually, it's not antenna not resonating since at low frequency antenna gain is very low here. Antenna, that is this peak only due to the losses present in the substrate. This is another parameter. This loss tangent versus frequency studied. Okay, antenna has very minimum losses at frequency 2 to 4 GHz. Antenna has high losses at low frequency, extremely low frequency, from up to some 1.7 GHz. Antenna has the high losses. This is radiation pattern of the proposed. There is a designed antenna. There is E-plan pattern. That is a co and cross polarization. Antenna achieves very good radiation value for the desired frequency. That is 2.4 GHz. This is the H-plane pattern of the that is radiation pattern of the proposed antenna at 2.4 GHz. This is a comparison of the antenna design using the nano material, that is hexagonal boron nitride nano ceramic material. Antenna that is performs well as compared to the other ceramic families. There is combination of nano and aluminum ceramic RT dorite substrate, and there's various substrate material from the ceramic families compared to this antenna design using hexagonal boron nitride ceramic substrate. Antenna performs well as compared to the other parameters, other antennas using different materials. So these are this antenna performs well. Okay, what I'm saying is that the antenna design using the hexagonal boron nitride is a good material. Is for the antenna design. Only thing with this material is antenna that is substrate is a rigid substrate. For wearable application, antenna should be very stretchable, right? So for that we cannot use this material as it is. So why nanomaterial substrate for 6G wearables? Okay, for these are some advantage. There is some key studies for 6G applications. So conventional substrate can fail to high frequency losses, poor mechanical durability, limited tunability. These are the problem with the conventional substrate materials. So wearable antenna should operate high frequency for 6G applications, and most importantly should have very low SAR. That is, especially absorption rate should be very low. Very smaller value. That is the main requirement for the antenna for wearable applications, and it should operate at very low power. So these are the reasons for using nanomaterial for these applications. So to satisfy these things, we have to use nanomaterials, okay, to achieve these things. So conventional substrates are rigid substrates, mechanically inflexible and uncomfortable for wearable use. Performance degrades under bending and movement. So pure polymer substrate, PDMS, PET, RTV, these they cannot use as it is because it has a there is poor electrical parameters. It results in larger antenna size and a limited miniaturization because it has a poor electrical parameter. That is what I say is that is epsilon r, it is very lower value, up to 2 only. So for any polymer substrate, it has epsilon r value of up to 2, but it is flexible. Thing is by using this substrate, we cannot go for miniaturization to the that is, we can scale the antenna up to lambda by 2. For any antenna can be scaled up to the size of lambda by 2. That lambda by 2 cannot be achieved by using this polymer substrate because it has a poor electrical parameter. So pure ceramic substrate, this high dielectric constant, that's a property of the very good property of ceramic substrate. It's a high dielectric constant and it's a good thermal stability. Why ceramic polymer substrate for variable antenna? It enables simultaneous electrical and mechanical property, and we can control this by using this ceramic and polymer. Okay, so by using ceramic, this is nanomaterial being preferred for as a patch for the patch antenna design. What I'm saying is polymer and ceramic can be composited. So advantage of polymer is it is flexible, but if you use ceramic substrate, ceramic material, that is rigid. So rigid substrate performs well. It has a good electrical properties, right? A high dielectric constant and thermal stability. That is polymer. It has a drawback of that is it has a poor dielectric constant. By making ceramic polymer by making substrate using ceramic polymer with suitable proportion, one can use this material for the variable antenna design, which enables simultaneous electrical and mechanical property can be controlled. Tunable dielectric constant for antenna miniatures that is done, and maintain this composite maintain flexibility and conformability under body movement. Improves the impedance matching and radiation performance, provides thermal stability in wearable antenna, offers design flexibility for compact wearable antenna. These are the reason for choosing ceramic polymer composite for wearable antenna design. These are the methodologies for preparing polyceramic material. That is, we need to pre-process. That is suitable. That is here polymer PDMS polymer material is being preferred. It has number of advantages. Suitable ratio of PDMS material and ceramic material is to be selected, and we need to prepare this substrate using powder metrology technique. That is possible. After preparing the substrate, we need to measure the electrical and mechanical parameters of the prepared substrate. Based on the electrical and the parameters measured for the prepared substrate, we can go for simulation of the variable antenna using the measured values of electrical parameters such as loss tangent and dielectric constant. We can do simulation using any tool that HFSS CST we can use. Then we can go for simulation that is validation of simulated and measured results. This is the process of making patch antenna using polyceramic material. And another case is ceramic powder synthesis can be done by another conventional method, mixing with polymer matrix, ultrasonic vacuum degazing, casting, modeling, curing, and advanced methods, PS coated ceramic. These are the another alternate method of making polyceramic composite materials. So from methodology 1, this methodology is pre-processing. Suitable ratio is to be arrived. Outer methodology technique should be adapted to prepare the substrate using compacting, sintering the green substrate in a high frequency furnace. By doing post processing of the prepared substrate, one can achieve the final version of the substrate. Then we need to measure the electrical parameters such as dielectric constant, loss tangent is to be measured for the desired operating frequency. Then that is a mechanical parameter that also be observed to check the suitability of the prepared patch for the wearable applications. Then we have to go for that is a design of antenna for the measured values using any one of the simulation tool. Then go for validation process. This is second method of another alternate method of making polymer ceramic composites. PDMS is mixed with the well agent. Then degaze using vacuum environment. Then ceramic powder is added with the suitable. PDMS is to be processed first. Then we need to add the ceramic powder with the suitable ratio. And then we need to mix. The mixer is fully degazed in vacuum environment, and mixer is left to dry and ambient environment for about 24 hours. In this way, we can go for making polymer ceramic compost. That is also possible. This is a prepared polymer ceramic composite. Actually, ceramic cannot bend. Actually, the rigid substrate only. By making polymer ceramic material, that is a polymer with the nano ceramic material. Nano ceramic has advantages. It has low losses. By making polyceramic material, we can make antenna. We can make it substrate is flexible and achieves good electrical and mechanical properties. So dielectric property, by using this method, by making polyceramic substrate, permittivity and loss can be controlled. So dielectric constant can be tuned, okay, from 2.5 to 10.5. So PDMS has very low dielectric constant. It's less than 2 only, but we can control by making suitable ratio. By selecting suitable ratio, one can achieve the dielectric constant to the any desired value up to from 2.5 to 10.5. Okay, RTB based can be done, can even up to 11.9. SDPE can be done using up to 2.5, 3.5 to 13.1. And the dielectric constant is very low. That is advantage of going with this nano ceramic material. It is 0.003, so very lower value because of the nano material inventions. It enables dielectric load that is also done. Key advantage is high FNR without sacrificing flexibility. That is advantage of using this material for patch antenna design. This is a flexible PDMS antenna, patch antenna using this material. This is in this method. Okay, by using this method is used for preparing the designing the patch antenna. This is the antenna using this prepared substrate. Antenna performs well this method also. So these are available in literature. So we can proceed with this methodology to achieve the that is by inventing. We can invent a new antenna substrate for the patch antenna design. And the thermal stability mechanism. Okay, polymer that is a polymer shows strong temperature dependence. Okay, and the temperature drift affect the antenna resonance. It's a problem with the polymer. So polymer compensation, the combination of polymer with opposite temperature coefficient that can be done. And paraelectric ceramic compensation, that is also been sodium titanium that will be done, and cancels the negative value of this polymer. So one can modify thermal property can be modified. Okay, antenna implementation using ceramic polymer substrate. So wearable microstrip patch antenna, that is polymer ceramic substrate can be based on this ceramic family, right? And the CST tool can be preferred. CST or HFSS tool can be preferred, and we have to achieve the good impedance matching at the that is a desired frequency band. And actually, pattern needs to be suitable radiation pattern we need to achieve for the desired specification. This is for the wearable antenna design principle for using the that is nano materials. Okay, nano material thing is we need to realize the suitable substrate. PDMS is the suitable polymer material, and the ceramic material can be chosen from the ceramic family. All these materials are that is proven in the literature, proven substrate for the patch in the literature. By using this combination, we can achieve the achieve the good antenna performance. For RFID and compact antennas, PDMS and barium titanium are preferred in the literature, and a significant antenna size reduction already achieved using these combinations. Good impedance matching that also be done by using this composites, PDMS and the barium titanium. For energy harvesting method, that is this ceramic family with RTB silicon composite substrate. This is a polymer substrate. Barium titanium with the RTM silicon already used for energy harvesting technique. Actually, it's alternative to PDMS substrate. Wideband operation that is done even up to 0.723 GHz, but rectifier efficiency achieved up to 57% output voltage of 1.35 volt. Even this materials not only find in antenna for conventional applications. It is polyceramic materials finds application wearable antenna that is already proven. RFID it is there already proven, and on-off energy harvesting that is also being preferred by this material. And the temperature stable antenna is also be possible by using this ceramic polymer materials. So still we have hope. Still we can do research. People can focus on this area to design antenna using ceramic polymer composites. So advantages of using ceramic polymer substances: tunable dielectric constant, low dielectric loss, mechanically flexible and lightweight, antenna miniaturization, thermal stability, compatibility with the wearable systems. These are advantages of using ceramic polymer materials. So current research trend in polymer ceramic is nano-structured ceramic fillers for improved dispersion and low loss. So we have number of there are so ceramic families as number can be used as a fillers. Okay, you can use as fillers since ceramic is a rigid, right? Ceramic is a rigid. We cannot use more material for the preparing the substrate. Should be very less. What I'm saying is we can use up to 20 to 30%. This percentage increases means which makes antenna is rigid. So we need this polymer ratio should be higher value. 70% polymer, 30% and ceramic. If you reduce the ceramic, what happens is we will miss the electrical properties. That is a dielectric constant and all those things. We cannot achieve the desired cases. Okay, that is a trade-off. Ceramic increase. If we increase the ceramic ratio, we can achieve the good electrical properties. But thing here is rigid. So antenna become substrate become rigid. So there is a trade-off. We can use a proper ratio of ceramic and polymer substrate material, and the multi-base porous composite architecture. That is another trend, and low-cost flexible polymer beyond PDMS. That is also possible for the another case. And the thermal compensated composite design that is also can be done. And wide and multi-band variable antenna substrate that is it's another trends in doing research. And integration with the energy harvesting with smart textile. These are the possible. That is. These are the way for that is we can prefer this area for doing research. So another material that is another composite material is a polymer textiles that is also being preferred nowadays. It's emerging. That is not textile antenna. We know textile antenna, textile fabric that is being preferred even yearly 2000, 2010. These textile materials are used as a substrate in most of the many people, many faculties, that is researchers doing research in RF domain. They know now polymer textiles also coming into picture for antenna design. What is polymer textiles? These polymer textiles are fabrics made from synthetic or semi-synthetic polymer material. These textiles are engineered at the molecular level to achieve the specific mechanical, electrical, thermal properties that natural fiber cannot provide. So we can modify the property by using polymer textile compounds. That is also possible. By dipping the textile substrate with a suitable material, one can modify the textile property. That is actually now people start doing research in this domain. So who are interested in RF domain, they can go for this type of research also. This and previous research. And the molecular structure composed of long chain polymer and repeating units. Engineering properties designed for specific that is functional requirements and advanced materials. Okay. So polymer textiles is there are a number of limitations of natural fibers. So modern requirements are smart and wearable electronic integration. That is a requirement. High performance application in aerospace, medical and biomedical application, extreme environmental performance. So these requirements can be done with the help of this polymer textile ceramic materials. So polymer textiles, so it has impacts in industrial, and there is a number of invention in technology and economical significance and scientific advancement. So all those areas, this polymer and textiles are used, that is preferred. Some of the key characteristics as electrical conductivity can be engineered from the insulating to higher conductivity. That is, electrical conductivity can be improved. Mechanical strength can also be we can also modify, and thermal stability even from lower temperature to extreme high temperature, that is also possible. That is by using textile alone it is not possible. By using polymer textile material, we can withstand the extreme temperature from -2 to -50 to 300 Celsius, and chemical resistance to acid based and organic solvents, and it is lightweight. And this durability, that is also long service life with the minimal degradations. This versatility and biocompatibility. These are the key characteristics of the polymer textile material for patch antenna design. Antenna, antenna is a polymer textile, wearable textile antenna. Substrate material can be preferred, and gain enhancement that is also be done since it has the low loss tangent. There is tan alpha, that is loss tangent can be measured loss tangent less than even 0.02. And bandwidth can be modified, and that is radiation and the impedance matching properties of the antenna can be altered using this polymer textile material for wearable antenna design. This is a manufacturing process. Polymer, we need to select suitable polymer. and we need to for textile is to be formulated, and we need to give some treatment, and we need to convert it to metallization, and we have to go for antenna. That is antenna design process. So suitable material is to be preferred, and textile is to be formed, and there are various methods of making polymer textile materials. There are a number of processes. So many inventions in the literature. Still, there is a scope. Too many means people started doing research in this polymer textiles. So we can do this. By using this technique, we can go. It enables inkjet printing and screen printing and even 3D printing. That is also possible using this textile polymer material as a substrate. It finds applications in wearable technologies and medical devices and aerospace and defense, automotive, sports, athletic, and IoT and smart homes. Finds applications. Any queries? I'm open to answer your questions. Any questions?
Participants who have any questions regarding today's session, you can post it in chat box.
So this research can be focused on in this area also. That is using nanomaterial for antenna design. That is a good area. People can prefer this area. Two of my scholars are doing research in this nanomaterials enabled antenna for 6G and IoT applications. Can be done. You can actually prove a lot of things in this. If nowadays, if papers are accepted only if you have the numerical analysis, so the numerical modeling is required for most of the journals are preferring this. But if you go with this way, people can there is researchers can easily they can done PhD work with they can do experimental work. That is also possible. So if you do experimental work in your research, it is appreciated by the examiners. So experimental work can be done in this domain. So people can prefer this domain for doing research. Any questions?
So kindly post your mail ID in the chat box, sir. On behalf of Department of Electronics and Communication Engineering, I would like to express our heartfelt gratitude to our esteemed resource person for delivering such a insightful and enlightening session on nanomaterial enabled wearable antennas for 6G and IoT application. The session provided us with a deep understanding of emerging nanomaterials, their integration in wearable antenna design, and their vital role in next generation 6G and IoT technologies. Your clear explanation, practical insights, and discussion on future research directions are greatly enriched our knowledge. We truly appreciate the time and effort you have taken to share your expertise with us. The session was highly informative and inspiring for both faculty members and students, sir. Thank you, sir. Thank you for your valuable time and representation.
My supervision. Anybody interested in doing research or to start research in this antenna design using nanomaterial, they can approach through Kavita madam. Thank you very much.
Sure, sir. Sure. So, can you post your mail ID in the chat box, sir?